wind turbine obviously has to be controlled. Why does it have to be controlled? Because at some point of time it has to be started depending on the velocity of wind, and then your objective would be to extract the maximum power from it. That requires certain control strategy. And then if the wind becomes too gusty, too high wind speed, then obviously the wind turbine has to be protected, and this will call for certain measures. For example, if it is too high a wind speed and you are extracting the full amount of energy out of it, obviously the gearbox, the generator will be overloaded and they might burn, and so that has to be protected. And finally, in situations like cyclones, so high a wind speed, obviously it has to be protected. So that will require certain strategies, certain measures for controlling the wind turbine. So today we will mainly discuss that. Now, the strategies for controlling the wind turbine becomes clear if we draw or make a plan for how do we plan to extract the power as the wind speed varies. As a function of the wind speed, what is our planned way of extracting the power? Following common sense, we can draw a graph like this. In this case, it will be wind speed in the x axis, meters per second in the x axis, and in the y axis it will be the power output. The power output will be in the y axis, say it will be in kilowatt or megawatts or something like that. Now, what will the curve look? Obviously, at very low wind speeds, will you be able to extract any power? No, obviously not. So, it should be starting at a specific wind speed, right, and this wind speed is called the cut in wind speed. The cut in wind speed. Below that, it might not rotate, or it might also rotate in the case that it attains certain amount of torque so that it can rotate freely, but no power is extracted from it. It is allowed to rotate freely. So, it can be both. In some wind turbines, there is sufficient starting torque so that it can start to rotate, but you do not extract any power out of it. In many modern and large size wind turbines, the starting torque is very small, so that it would not start at all by itself. So, at this point of time, you start extracting the power when you decide that okay, my cut in speed has been reached, that means the wind speed is now sufficient to extract power. Beyond that, obviously there will be no power output before that. Beyond that, what happens? What should be the characteristic like? Beyond that, there will be a range when the wind speed is moderate. If you extract the full amount of power out of it as much as you can within the limits of the Bates theory, then at least the generator, the gearbox, these things will not be overloaded. So, what will be the strategy? Obviously, to extract maximum power. Now, if you extract the maximum power out of it, then what should be the characteristic like as you vary the wind speed? It will vary in proportion to the power contained in the wind, and the power contained in the wind varies cubically with the wind speed, right. So, obviously, the amount of power output will vary like this, and it will be a cubic characteristics. Fine. At this point, if you extrapolate, it should go to 0 at 0 velocity. So, here it is P proportional to V cube or V infinity cube. So, that is the characteristics. and what we will have to do in order to attain these characteristics, we will discuss that. But as the wind speed increases, there comes a particular state when if you extract the maximum possible power output, that is the rated power of the generator. Every generator has a rated power, every motor has a rated power, everything has a rated power. So, it has reached at this point where it is the rated power. And it is reached at a wind speed, that is the rated wind speed. So, that means when you construct the wind turbine, you construct in such a way that if the wind speed is this much, the power output will be that much, and that is the rating of the machine. When you did your laboratory experiments, you have found that every machine has a nameplate, and on that nameplate a rated power is written. What does it mean? Can't it produce less than that? Yes, of course it can produce less than that. But if it produces more than that, then the wires overheat, they may burn, the insulation may go. So, overheating will not be desirable. So, that is the concept of the rated power. It comfortably works at that particular speed and particular power. What should we do as the wind speed increases further? Obviously, you should not exceed the rated power, or even if you do, you can do only by 10% or more, not more than that. So, what should be the strategy? Ideally should be to flatten the characteristics. That means, at this point it should be a flat characteristics. Even if the wind speed increases, the power does not increase, and it becomes level at the rated power output till a certain wind speed, and this at this particular wind speed, the wind speed is now too high for the protection of the wind turbine itself. If it is too high, then what happens? At some point of time, you have to engage your protection mechanism. That means, you cannot allow the wind turbine to rotate any further, you have to stop it. Why? Because if it does not, then the stresses will be so high that the wind turbine blades may break. So, at this point it has to be stopped. This wind speed is called the furling wind speed or cutout wind speed. So, this is your rated wind speed. You will find that normally the wind turbines are rated to work at that speed, producing the rated amount of power. At that point, at this point, you will find that this is still working at the maximum power level. Maximum power level is at the maximum efficiency, maximum CP, power coefficient, and it is producing its maximum possible power output. So, this is the optimal operating point of the turbine here. So, that is the rated wind speed. In the specifications of a wind turbine, normally the rated power is specified and the rated wind speed is specified. One energetically illiterate person will assume that if I have installed a wind turbine there with a rated power, say 1 megawatt, then I am through, I am producing 1 megawatt. No, because ultimately what you produce depends on how much the wind, how much wind is coming, and unless the wind turbine is properly matched with the characteristic of the site, it may not produce optimally, which I will come to later. But first let us understand how to obtain this kind of characteristics. This is the standard wind turbine characteristics. Only let me also mention that here we have argued that you should not go beyond the rated power output, right, which is a logical argument. You should not go beyond the rated power output, but there exist certain generator configurations which can allow one to extract say 30 to 40% more power output without overheating. What these are, I will come to that later. But there exist this kind of electrical conversion mechanisms by which you can do that. If you can do that, then you can relax and sort of go this way, but you of course have to stop it at the Furling wind speed. So, here we get more power output if you can install that kind of generators, but normal the run of the mill generators will have a definite rated power level. So, we will proceed with the assumption of these characteristics, but you should also know that it is possible in some generators to go beyond that. Okay. Let us start. What means do we have at our disposal? How can we do this control? There are in the main 4 things that we have. 1, controlling the pitch angle. 2, controlling the power output. Pitch angle control controls the mechanical power input. Electrical power output can be controlled, which I will discuss in somewhat details later. I will not be able to go into great details because you have not studied electrical machines and power electronics to that extent, but nevertheless you have to presently assume that it is possible to control the electrical power output by some electronic means, power electronic interfaces. 3, what is yaw control? I will come to that. And fourthly, braking. Let us come to this one by one. Okay, let us start from yaw control, because when I talk about this, when I mention this word yaw, you need to know what it is. Yawing essentially the means of orienting the wind turbine in the direction of the wind, that is yaw. That means a horizontal axis wind turbine has to be oriented in the direction of the wind, right? It has to be turned, and in the last class I have shown that the whole head of the wind turbine sitting on top of the tower is like a turntable. It can rotate, and there is a servo motor doing this turning business. So, that is a yaw control. Now, this yaw control can also be used, at least theoretically, for controlling the power output, because if there is a wind coming this way and if you do not want that much of power output, simply orient it away from it. You might argue this way. Actually, it is possible, theoretically possible, but never done. Why? Because if you are looking away from it, then all the blades that are turning, they will see the wrong direction of the wind, and as a result they will produce stress, which is undesirable. So, and moreover, if you use yawing as a control mechanism, you will have to all the time move it, and this huge structure sitting on top of a tower, turning it is not easy job. It requires power. Not only that, it also makes sound. You can hear that sound, yawing. So, it becomes somewhat undesirable to do that. But nevertheless, you should know that it is a control mechanism in your hand. But there is another issue here as related to the yaw control. Suppose a wind turbine is situated like this, and the wind is coming this way. It is possible. You can design the wind turbine so that it could come this way, or you could also design the wind turbine so that it comes this way. If it comes this way, it is called a downwind turbine. And if it is downwind, can you do a yaw control? Do you need to do a yaw control? No, because it automatically turns. Can you see that? The thrust force will act on the blade, right? The thrust force will act on the blade and the pivot is here. So that if it is disoriented, the thrust force itself will orient it back, right. So, if you have a downwind wind turbine, you do not need to have a yaw control, but the disadvantage is that then the tower shadow effect will be larger, because here the tower is there and the tower will produce a blockade in one position of the blade. So, that will produce a torque pulsation. So, some companies prefer downwind wind turbine because you do not have to have yaw control, but some other companies prefer a upwind. If it is upwind like this, then you have to have a mechanism for yaw control. Okay. So, in the downwind wind turbine, the advantage would be the whole mechanism of turning the thing will have to be unnecessary, while in upwind wind turbine they will be necessary. Clear. So, that is the point about yaw control. And yawing normally is controlled. There are two possible ways. You need to know which direction is the wind coming from. Now, either if it is a wind farm, that means there are places where, because of the advantage of a high wind speed, a large number of wind turbines, say maybe 1,000 of them, are put in a single place. So, the whole thing works as a system, and then it is not necessary for each one to detect the direction of the wind, because all of them will face the same wind from same direction. So, there can be just one place where the wind direction is sensed and the sense is sent to all the wind turbines to do the orientation. In that case, there will be a central controlling station from which the control is actuated. Else, you can have small perpendicularly directed, that means this way, a small again wind turbine, something that is oriented at orthogonal direction to this one, which senses whether the wind is coming from this direction or it is coming from sideways. If it is sideways, then this will rotate and will give the error signal, which can be used to turn the whole turntable. Okay. So, for singly operated wind turbines, this is the option, but for large wind farms, you have a better option available. Clear? So, that is the point about the yaw control, and as I told you, yaw control can theoretically be used for controlling the power output, but it is actually not done, because it produces loud noise and stress on the blades. What it leaves us is the issue of pitch control. Now, about that we have understood a few things. Firstly, we have understood in the last few lectures that the tip speed ratio versus Cp, power coefficient characteristics, is like this. What does it mean? It means that the maximum Cp, that is where we want to operate in this zone, we want to operate at maximum power coefficient, and that happens at a specific value of tip speed ratio. And the tip speed ratio is the speed of the tip, which is related to the angular speed of rotation, divided by the wind velocity. So, as the wind velocity changes, what should we do with the speed of rotation? It should change proportionally, then only you can keep this constant. Okay. So, as the wind speed changes, that is a variable thing that you have to cope with. As the wind speed changes, you have to vary the speed of rotation, the omega, the angular velocity, exactly in proportion to the wind speed, right, and then only you can reach this. Seen from the point of view of individual blades, we have seen that it works at its maximum aerodynamic efficiency at a specific value of the angle of attack I, small I. You have seen that, right. What was the logic? The logic was that epsilon should be least possible. From the airfoil characteristics, we get the value of the lift coefficient versus I, the drag coefficient versus I, and from there we find the least value of epsilon. How? By drawing the tangent, or simply you divide the CD by CL and draw a graph. So, you draw a graph CD by CL and you get the minimum point, that will be corresponding to a specific value of I, and that angle of attack should be maintained. That is the logic from the point of view of each airfoil. Now, in order to maintain this I, what is this I? That was, if you remember, this the velocity parallelogram. This was our V and this was our minus U, and this was our relative wind, and this was capital I, and the small I was capital I minus the pitch angle, right, just to recall. So, if we want to keep the small I constant while the capital I varies, why? Two reasons. First, V varies with the wind speed varies, and secondly U varies. At this point of time, we are not considering the variation from the inside edge to the tip. We have already seen that varies, and for that we need to give a twist. But here we are considering the speed of rotation of the whole thing, and as the V changes, I changes, capital I also changes, but all the time your objective should be to keep small I constant, and that can be done by continuously varying the alpha pitch angle. So, the pitch angle has to be varied, right. In what way? Okay, this is theoretical fine, but if you want to go back with some sort of roundabout idea, then you might think this way, that here is my airfoil and I should orient in such a way that the wind actually is seen to be coming from this direction W. So, that the wind sees the least area, and if it sees the least area, it will produce the least drag force. Okay. If the drag force is reduced, logically that should be give me this point, least drag force. So, you should always try to orient the airfoil in the direction of the relative wind. So, that is the logic. In any case, you have understood that this can be achieved only by continuously varying the pitch angle, and the pitch angle, you imagine that this whole blade, here is the center, here is the axis, and here is the whole blade, say. Then at this point there has to be a motor situated that can turn it like this. Okay. So, these blades are not actually firmly attached to the axis. There is a scope for this to turn, okay, and that is the pitch angle control. So, at these points there would be motors, servo motors doing this turning business. What will the logic? What will the logic be? The moment I say that there has to be a servo motor and it should turn, then you have to think of how to control it. How to control it means, theoretically I will always keep I constant, fine, but ultimately you have to devise the whole thing in terms of some kind of a reference signal, some kind of a error signal, and finally you have to do the control. Are you really sensing all the time what is capital I? No. Are you really sensing all the time what is small I? No. because in that case you have to have sensors along the blade, which you cannot really do. So, how to do that? There are two ways of doing this. One, you have seen that the CP versus TSR characteristic reaches its peak at a specific value, at a specific TSR. Now, the TSR signal, that means the value of the tip speed ratio for which maximum CP is attained, that can be measured and kept as a reference, okay. And as the wind speed varies, that can be sensed, there is no difficulty about it. If it is a wind farm, there can be a single central station at which the wind speed is measured continuously. So, you have a sense of the wind speed. Sense of the rotational speed that can also be obtained very easily, because the turbine is rotating, you can always sense what is the speed. So, all the time in real time you can measure the TSR, right. Now, if you find that the TSR is less than the reference TSR here, that means I am now operating somewhere here. What has to be done? Something has to be done in order to move it this way. That means you essentially have to speed it up, right. You have to speed up the wind turbine. How can you speed up the wind turbine? Then you pitch it, and if that results in a the increase of the speed, you know that you are pitching in the right direction. Okay, that means you change angle, and if it changes like this, you know that you are going in the right direction. If it is too high, then you have to go this way. So, there will be essentially different ways of orienting the pitching. Clear? There is another thing in our hand, I will come to that later, but essentially the pitching should aim at this. The change of the pitch angle should aim at this, should aim at keeping I minus alpha constant. I should be the alpha should be so changed that this is constant, this is there is another lever in your hand, that is, as I told you, the control of the power output. Now, if power output is controlled, that means from the wind turbine, there is a mechanical power going, and then I am schematically drawing, there is a electrical power, and this electrical power, this is Pm and this is Pe. So, a mechanical power is going into the generator and the electrical power is withdrawn. Obviously, the speed will depend on the difference between the two, right. Imagine it is rotating at a specific angular velocity omega, and now the Pm the mechanical power remains constant, but you deliberately reduce the electrical power. Okay, what will happen? There will be a difference between Pm minus Pe. Okay, if there is a difference in Pm minus Pe, then what will happen? Then you can write the equation as J, the angular moment of inertia, times d omega dt is equal to Pm minus Pe by omega. You can easily see that there will be a positive value here, the speed will go up. Okay, there will be positive value here, the speed will go up, because this is positive. And how much will the speed go up? You can integrate this. You will write half j. After some time, this speed is say omega 2 square minus omega 1 square. This happens over a time period of T1 to T2. Pm minus Pe times dt. Okay. So, if you allow this to be positive, after some time this it will change, the speed will change from omega 1 to omega 2 and you will have a larger speed. So, as I told you, you need to operate, where did I keep it? You need to operate here. If say you find that it has come here, right, that is another thing that you can do. You allow less amount of power to come out. As a result, what will happen? It will speed up and it will come back here. When it has come back here, you have no more power available. Then you again increase the power output, but by then it has reached here. Clear? So, all the time you can work in the neighborhood, in the vicinity of this maximum power point. Here is the maximum power point. So, the take home message is that the pitch angle control will be controlled by this. Even if you do a pitch angle control, it may or may not work at the MPP. So, in order to get at the MPP, you additionally have to control how much amount of power you are taking out of the machine and ultimately operate here. And this power output of the machine, PE, that can be controlled. Presently, at the present time, you just take it from me that it can be controlled, and how it can be controlled, I will come to that later. Okay. Yes, of course, in some generator configurations it can be controlled, not all. So, in some generator configurations you have this additional lever in your hand, but not in all generator configurations. In cheaper electrical systems you do not have this control. There is a problem of working this way. What was the logic I said? I said that the logic is that you store in a microprocessor, the controller is driven by a microprocessor, in that you store the value of the tube speed ratio. And depending on that you do your control, fine. Logically it is simple, but the practical difficulty is, firstly, how do you find out this for a big wind turbine? It is not easy. Secondly, that means you cannot put the big wind turbine into a wind tunnel and do the testing. So, it has to be somehow, this has to be obtained. Supposing somehow you obtained it, but this does not remain the same throughout its lifetime. Why? Because the blades that are initially smooth will slowly become rough, you can't help it. As it becomes rough, the maximum power point, that means the value of TSR at which the maximum power point is reached, that also will shift. So, even if you can obtain it for a particular time, that means when it is first installed, you cannot logically guarantee that it will remain the same throughout its lifetime. Then what to do? That is why some of the more modern control systems incorporate a different control strategy. That control strategy is something like this. Notice that it is a one humped curve and the peak is smooth, means differentiable. What is the character of, what is distinctive character of this peak as compared to any of these points? At any of these points, if you change the TSR, the CP changes, but at this point if you change the TSR, the CP does not change. See, right, convinced? That can be used as a means of obtaining the maximum power point. What to do? Supposing you are here, you reduce the power output of the electrical system so that its speed goes up. As the speed goes up, the system senses that now my CP is going up. If it is going up, then I should reduce the power output even further so that it goes up further, that I am going in the right direction. But as it reaches here, you change it even further, it does not change, right. So, if you change the TSR, tube speed ratio, and if as a result the power coefficient does not change, you know that you have reached that point. Now, just build this as a continuously checking logic. That means, if the wind speed changes, everything changes, the speed has to be changed, the pitch angle has to be changed, everything has to be changed, fine, but ultimately it will again get back to its maximum power point by the same logic. At the different wind speed, it should again check, am I working at this point? That means if I change my TSR now, am I now getting into the this point, this valley? So that is another logic by which this is done. Clear? Okay, so we have more or less understood what can be done here in order to obtain the maximum power output, right. Again, to repeat, we have essentially two levers in hand. One, the pitch angle control, which controls the mechanical power input. Two, the power electronic control that controls the electrical power output, and with that you ultimately obtain this. The logic for controlling the pitch angle should be to keep the I constant at the optimal value, and the logic for varying the power output through the electrical means should be to obtain the maximum power point in the CP TSR characteristics. What about here? How to flatten it? You would notice that this is the region where the wind contains more power, but you are not extracting that. How can you do that? Here also you have, but here remember, here it cannot be done by electrical means, because electrical power output's maximum value you have reached already. So that if you want to reduce the power, the speed, you cannot simply do that by extracting more power out of it. Why? Because you are already at the peak, right. So at this point you have to do it mechanically, and mechanically how? There are two ways. One is where as you have seen that so far we were controlling the pitch angle in order to obtain the maximum power output. Suppose we now deliberately do it wrongly, what will happen? It will give less power output. So the one way is to pitch it in the wrong direction, so that the power output reduces. So that is one means available in your hand. That means here the power output will be kept constant, the mechanical power output will be kept constant by changing the pitch angle in such a way that it gives out less amount of power. But always remember, it has to see that it is there, it should not reduce further. So what pitch angle gives what pitch angle gives the proper power output, that is to be judged. So all the time the power output is measured, and depending on the pitch angle is controlled. Okay, what will happen? If you change the pitch angle very badly, it will dip. The moment it dips, the moment it goes below the rated power, you know that you have changed it more than you should, so you can change it. So this can be built into a sort of continuously operating logic in the control mechanism, so that you change the pitch angle in the wrong way. This is called this part is called stall part, where you are not aiming at utilizing the complete power that is available in the wind, this stalling part. And there are two ways of stalling it. One is called the active stall, and the other is called passive stall. Active stall is what I just described. That means you change the pitch angle in such a way that the stall happens. It does not extract as much power output. But in that case, you have to have the pitch control mechanism operative. As I told you, for small wind turbines, pitch control mechanism is often does not justify itself, right. If the pitch control does not justify itself, you do not have the pitch control, then you cannot do this. Then what? Then still you have to protect the wind turbine. There is still a mechanism available for it. That is, as I told you, when we drew the rectangle of the velocities, this was the velocity of the wind and this was the velocity of the blade, and we drew this, and this was our I. just let me rewrite I is equal to I minus alpha. Alpha is fixed now. Small wind turbine, we do not have the scope of varying the alpha, so that is hard fixed. Then what happens? As wind speed changes, it becomes larger. This capital I changes. Okay, it becomes like this. If the capital I changes, the small I also changes, which means it is no longer operating at the optimal point. This means that even if you do nothing, the output power might vary, will vary, and the whole thing can be so designed that it, if you change the wind speed beyond its rated speed, then it automatically drops. Clear? That means at the design stage of the design of the blade itself, this whole logic can be built into it, so that as the wind speed varies, wind speed changes, increases beyond the rated value, the I changes such that the power output falls. Okay, that is called the passive stall. So, passive stall is normally used in small wind turbines which do not have the active stall mechanism, but otherwise the active stall is the same as pitch angle control, but here the objective of the pitch angle control is stalling rather than obtaining the maximum energy out of it. Okay. If you have the active stall control or the passive stall control, the energy output will be something like this. You want it to be flat here, but it becomes so it becomes something like this. So here it is the wind speed, and here it is your power. Why this hump? Because this is the range zone in which you are essentially shifting from this mode of operation to that mode of operation, and there is a twilight zone where the wind contains a lot of power, but you have not yet shifted completely to this. So, if you have a passive stall, then what will happen? It will still increase for some time, and then as the angle changes much, it will fall, and at this point again it has to be completely stopped. Stopping, that means at very high winds, how to stop it? Again there are two ways. One, you change the pitch angle in completely wrong direction, so that it produces absolutely zero torque. That is also possible. That means the wind is coming, you simply change it in such a way that it produces zero torque. If it produces zero torque, it will stall, it will completely stop. So, that is one way of stopping it, but still normally after having reduced the speed that way, one operates a mechanical brake, like the same brake as you have in a car. Mechanical brake, finally it completely stopped. When a gusty wind comes or there is a prediction of a cyclone or something like that, the whole wind farm has to be completely shut down. You cannot allow it to rotate, because if it rotates, then it may go off. There are other reasons for this. Supposing the wind turbine is connected to the electrical line from here, the 3-phase electrical line is going, and in an electrical line that is connected to further networks, the grid, there can be a shutdown of the grid itself, right? There can be shutdown of the grid itself. That means you have seen load shedding, you have seen that there is a complete failure of the grid, or there can be some kind of a electrical failure in any of these lines. Then obviously this line is cut off. PE suddenly goes to 0, but PM is there. What will happen? It will increase speed endlessly, and the blades will simply break. So that also has to be stopped. So there has to be a protection mechanism, so that if the speed of rotation goes beyond a certain value, then the braking mechanism must spring into action and stop it, because these are not uncommon. Breakages of the electrical line are not uncommon. You have seen that even though you have a reasonably secure power supply, you do have load sheddings. Similar things can happen here. If this line does not have power, you are gone. So, these are other control strategies you need to have. Clear? Okay, so we are more or less we have covered all this: pitch angle control, electrical power output. The details I will come to that later. Yaw control and braking. Obviously, in all these controls, one important input is the measurement of the wind speed, or suppose you do not have any wind turbine anywhere, but you feel a particular place is windy, and you say that now I want to utilize this wind in order to generate power. Obviously, being engineers, you cannot really say, oh, when I stand there I feel it very windy. You cannot say that. You ultimately have to quantify that. That means you have to measure wind speed. How to measure the wind speed? There are exactly three different ways of measuring the wind speed. One, okay, if there is anything that changes with the change in wind speed, you can use that as a measurement instrument. But there are three things that one normally does. One is called the Robinson cup anemometer. It is called the Robinson cup anemometer. Speed measurement, wind speed measuring instruments are called anemometers. Anemometers are wind speed measuring instruments. Now, the Robinson cup anemometer is, wait, before coming to all this, let me also tell you that all these control strategies that I have talked about, actually this and this will work only for horizontal axis wind turbine. For vertical axis wind turbine, like I have already talked about this Darius rotor. In the Darius rotor, obviously there is no question of yaw control, because it is symmetrical in all the directions. So, it does not depend on the direction of the wind. Yaw control is out of question. Pitch angle control is also out of question, because here you cannot change pitch angle. The airfoil is directed like this and it is simply there. You cannot change the direction. So, pitch angle control is not possible in case of the Darius rotor. In that case, what can you do? First, you can still control the electrical power output, and two, the advantage of the Darius rotor is that at very high wind speed it stalls automatically. At very high wind speeds, if you again draw the force parallelograms, you will realize that at very high wind speed the force reduces. That means all the time you have the force created like this. This is moving this way. So, this is your u, and there will be some kind of a v, and you have to draw the parallelogram by completing with minus u. So, you have got this, and you will have the speed, and this is the Fd and this is the Fl, right. So, the actual force that produces the torque is the difference between this and this. This will produce the torque and this will try to resist. The difference will actually produce the net torque, and if this becomes much larger, you will find as it goes around this whole circumference that the net torque becomes almost 0. So, that at very high wind speeds, at very low wind speed it has no torque, at very high wind speeds also it has no torque, at 0 u it has no torque, only at a optimal condition it has torque. So, it has an inherent protection, does not break by itself, clear. But also the disadvantage is that you do not have the active control mechanisms by which you can extract the maximum power. You have to rely on its own inherent characteristics. Okay, now Robinson cup. The Robinson cup anemometer is somewhat similar to the Savonius rotor. What was the Savonius rotor? Where you had cut two cylinders into half and joined them. Here also you do not have to cut cylinders, but it is a combination of two small or three small hemispheres like this. I am drawing 4 of them, small cups. So that as wind comes, it produces differential torque in the two sides. As a result, it turns this way, and this rotation can be measured either by having a small tacho generator connected with some kind of a electrical measuring device. That means it produces a voltage which is proportional to the speed of rotation, or you can have a one of the other. Nowadays one normally uses digital measurement. In that case, there is a the simple way of measuring is that you have a disc with holes in it. You shine a light so that the light goes to only these holes, and there is a detector at the other end, so that if this fellow rotates, the detector will detect, right, and you can easily find out its frequency. That will be proportional to the frequency of the wind. So, the Robinson cup anemometer is essentially a measuring instrument that relies on the thrust force produced by the wind, so that it rotates, and that rotation is ultimately measured. Normally it is measured as a electrical sensing. Nowadays it is always measured as a integrated instrument that also does the data logging. That means the data is continuously logged, so that at the end of the day you can insert a pen drive and get the data for the last 6 months and get back home and analyze the data. Okay. There are cheaper versions in which you do not get the actual wind speed variation over a length of time, but you have the average wind speed measurement. There is a display where the average wind speed is displayed, and the measurement of the average wind speed is done by this fellow automatically. So, you put it in a remote location, go there periodically and read off the average wind speed. There are also instruments available like that. So, one thing is that you can, through this kind of instrument, continuously measure the wind speed and then use that as the input to your analysis. So, in the next class we will start from there. That means what can you do with this kind of a measured data? What will the data look like? After you have got the data back from that source, that place, as some kind of a data set that you bring in a pen drive and plot it, what will it look? It will look a very, very erratic and wavy, unruly waveform. Something has to be done in order to extract meaningful things out of it, because ultimately this data has to be used in order to analyze how suitable a site is, or if you install a particular wind turbine in that site, how much power is it going to generate. All this very, very technically meaningful information has to obtain from this kind of a very unruly and wavy data. There has to be a large amount of processing to be done with this data. We will come to that mathematics in the next class. Okay.